Hello, welcome to Nova Core Physics. In today's video, I'm going to show you how to solve this projectile motion problem. A long jumper leaves the ground at an angle of 20.0 degrees to the horizontal and at a speed of 11.0 meters per second. We are to calculate how long does it take for this jumper to reach the maximum height. Also, we are to find what the maximum height is, and finally, we are going to calculate the range of this jump. In this problem, take acceleration of gravity to be 9.8 meters per second squared and also neglect air resistance. Now let's look at the solution. So to solve this problem, we need to first identify that this is a two-dimensional motion problem and it involves a long jumper jumping off the ground at an angle of 20.0 degrees to the horizontal with initial speed of 11.0 meters per second. So the first thing we need to do is to identify our coordinate system. So in this case, I'm going to use the convention where we have any vector quantity upwards is positive and then downwards is negative, and also to the right is positive and then to the left would be negative. So since this is a two-dimensional motion, we are going to have the x component of the motion and also the y component of the motion. So to set it up, I have my vertical component of the motion and then the horizontal component of the motion. I label the vertical component as y and then the horizontal component as x. Now I can place my origin, that is the point of launch of this long jumper, at this location. So if we place the long jumper here, he launches off with an initial speed that makes an angle of 20.0 degrees to the horizontal. So we can have it here as our V0, that is the initial speed. And this speed makes an angle of theta to the horizontal. Since we do have acceleration of free fall acting vertically downwards, we are going to have this trajectory to be a parabolic trajectory. In that case, we are going to have something like that until he hits the ground. With that being said, from the point he hits the ground to the origin, we will have our delta x, which we also call the range. At the same time, in the vertical component of this motion, he is going to travel a vertical height until he reaches a maximum height, delta y. And at this maximum height, the velocity along x direction is constant throughout the motion. So at this maximum height, the velocity along the x direction is going to be the same as the initial horizontal speed, and the velocity in the y direction or the vertical velocity is going to be 0. Now we need to resolve this initial launch speed into horizontal and vertical components for the motion respectively. To do that, we need to see that this is a vector pointing in the direction of theta. We can develop a right triangle from this point down to that point. So we can have that side to be our V0y and then we will have V0x. You can see a right triangle with the hypotenuse V0 and then the opposite side V0y and the adjacent side V0x. Applying SOHCAHTOA, we can find the V0x, which is the initial horizontal speed of this motion, to be V0x equals the hypotenuse, which is V0, times cosine of the angle theta. In the same sense, we can find the vertical component of the initial speed, which would be V0y equals V0 sine of the angle theta. So we can plug in our initial speed because from the problem we are given that the initial speed is 11.0 meters per second and then the initial launch angle is equal to 20.0 degrees. With this we can find the initial horizontal speed as well as the initial vertical speed. So with that we have V0, which is 11.0 meters per second, second, and then cosine of the angle, which is 20 degrees. So this is going to give us 10.3 meters per second. In the same sense, we will have 11.0 sine of 20 degrees, and this is going to give us 3.76 meters per second. So this is our initial horizontal and vertical speeds. Now we are in the good position to solve for the maximum height reached. To solve for the maximum height, we need to refer to one of the kinematics equations of motion for the vertical component. Looking at the data that we have, we know g to be 9.8 meters per second squared. We know the initial vertical speed, which is 3.76 meters per second. We also know the speed at the maximum height to be 0. We can apply Vy final equals Vy initial plus gt. So this time is going to be the time it takes this object to reach the maximum height. The next thing we can do is to isolate this time it took it to reach that maximum height. To calculate the time it took to reach the maximum height, we can move this v0y to the left hand side. So subtracting v0y from both sides of the equation, so v0y, and also subtracting v0y here. This will take that out, so you have vy final minus v0y equals gt max. So now we can divide both sides by g, and then this g cancels out this g, and we have t max to be equal to vy final minus v initial in the y direction divided by g. Now at the maximum height, vy final is 0, so that goes to 0, and then we have negative v0y. Again, v0y is now v0 sine of theta, and we just found it to be 3.76 meters per second. So we are going to have t maximum, time it took to get to the maximum height, to be equal to 0 minus 3.76 meters per second divided by, so negative 9.8 meters per second squared. Now we can see that the two negatives cancel out, and then we will have t max of 0.38 seconds. The time it took this object to reach the maximum height is 0.38 seconds. Next, we need to calculate that maximum height. So let's see how to calculate the maximum height. We found out that the time it took to get to the maximum height is 0.38 seconds. Now let's calculate for that maximum height. So the maximum height reached, we can use v final squared, so that is vy final squared equals vy initial squared plus 2g delta y, where delta y is nothing but that maximum height reached. So at the maximum height, we know the final velocity is 0 at the maximum height, and then we know the initial velocity, so we can isolate our delta y. To isolate delta y, again we subtract vy naught squared from both sides, so that is going to be vy final squared minus vy initial squared equals 2g delta y. So now we divide both sides by 2g. The 2g's cancel out, and then we have delta y, which is the same as the maximum height, h max, be equal to v final squared minus v initial squared divided by 2g. H max is going to be, so v at the maximum height is 0, so again we have 0 minus the initial vertical speed, which is v0y. We already calculated that, so that is 3.76 squared divided by 2 times g, which is minus 9.8 meters per second squared. So evaluating this is going to give us the maximum height of 0.72 meters. We just calculated the maximum height to be 0.72 meters. Remember, I did mention you can also use the time taken to reach the maximum height to calculate the maximum height, and in that case you need to use the displacement equation, which is delta y equals 1/2 gt squared plus v naught yt, because you now know the time you can use to calculate that maximum displacement. So that is another approach, but I find this one more straightforward. So let's look at the final part of this problem. So we just found the maximum height, which is h max equals 0.38 0.72 meters. And then finally, we are to determine how far does he jump. We are to calculate for the range for this jump. So the only range equation we can have is r, or delta x, equals the initial speed v naught x times time. But this time here is the time it took this projectile to leave from this point to this point. However, we only know the time it took the long jumper to leave this point to the maximum height, which is halfway here. So in that case, we have that the time of flight is going to be this time. So this time t should be equal to 2 times the time it took the long jumper to get to the maximum height. So with that, we can say that so the time is 2 times 0.38 seconds, and that gives us the time is equal to 0.76 seconds. So with this time, we can then use it to calculate the range of this motion, because we already know v naught x to be 10.3 meters per second. So the range, or how far he jumped, is going to be v naught x, which we already calculated it here. So 10.3 seconds, so 10.3 meters per second, and then times the time of flight. In this time, or in this case, the time it took the long jumper to leave this point all the way to that, not to the maximum height. But because this is a symmetric problem, it will take twice the time it takes to reach the maximum height for the whole motion. So 2 times that time it took to the maximum height gives us the time of flight, which is now 0.76 seconds. We can see the seconds cancel out, and then the results comes out in meters. So the range is going to be 7.83 meters. Yeah, that is the end of the problem. We found the time it took him, or how long it took him to get to the maximum height, to be 0.38 seconds. The maximum height itself to be 0.72 meters. And also the range to be 7.83 meters. If you are new to this channel, this is a physics problem solving channel. Hit the like and share, and also subscribe button so that we can reach maximum amount of people, and also enjoy the rest of your day. And I'll see you in my next video.